All right, this is section 13.3. This is on partial derivatives. So the goal of this section is to introduce what a partial derivative is, do some examples, talk about notation, and understand what a partial derivative can represent. So for a little intro, just a reminder as to what a derivative means. Like back in calculus, there's a definition, and then there's sort of a visual understanding. So in calc, let's say 1, 1, and 2. If we take the derivative at a point, this can be officially defined as the limit as h goes to 0 of f of x plus h minus f of x minus h. And what this equals, this is the slope of the tangent line. At x. So for example, if we have something like if f of x is x squared, then if you take the derivative, and then for example, you can take, say f prime at 1 and get 2. We can say this means, if we draw a picture of this, terrible x-axis, but that's right. So if I draw that graph, this is f. If we go to the point 1, 1, 1, that's the point on the graph of f. If we draw the tangent line, that has a slope of 2. Now what that means is instantaneously, if x increases by 1, y increases by 2, right, on this tangent line. That's what's going on there. So then with a function of, say, 2 variables, we could say, how about with a function like f of x, y, right? It doesn't make any sense to take the derivative because in the calculus sense, we're looking at basically if x changes, how does the function change, right? So writing, say, f prime of xy is nonsensical, right? So over here, in this example, x is changing. So with a function like f of xy, we can ask 2 questions. So with f of xy, we could ask the following. We could say, as x increases, how does f change? Or we could say, as y increases, how does f change? And if you had more variables, you could do that too, right? If we had, say, f of xyz, we could ask, as z increases, how does f change? All right, so over on the left-hand side, here, what we said over here again is as x increases, how does f change? And so over in the second case, we have more things that could be changing. So what we need is, we need to sort of look at what the derivative could be, right? Like, how could we define this? So how could we create a definition that makes sense? So what we'll do is this. I'm going to talk through this for the situation where x increases. And then we'll have some notation. and then we'll sort of see the parallels for if y changes, if z changes, etc. So I'll just do the definition of the first case, like really officially, just so we see, do some examples, and then we'll sort of work through the other cases and see how it all works out. So I'm going to clear the screen, but the thing to keep in mind is we're interested in looking at these variables, x and y, and what happens to the function as x changes and as y changes. And if we have f of x, y, z, also we can see what happens as z changes. So 2, we'll say partial derivatives. So this is what we can do. Given f of x, y, this is what we'll do. We'll say f sub x of xy. This will be what's called the partial derivative of f with respect to x. So just take a second to digest what that means. It's saying, like, it's sort of like saying the derivative of f with respect to x. So what we're doing here is we're going to look at what happens when x changes. And the official definition, which we're not going to use, but it's worth giving, is this. So take a second to read through this. This looks somewhat like the definition of the regular derivative, but what we're saying in this definition is we're saying that we're only interested in x changing. Right? Only x changes. Y does not, right? I have a y here and a y here. Those are the same, right? So what we're essentially saying here is we're examining what happens as x changes but y doesn't. So we're examining what happens as x changes but y stays the same. Now, this is not like a deep theoretical calculus course, so we don't need to go back to this definition. Instead, we can think about what this is actually saying, right? So this is like saying, what's the derivative, but treat x like the variable, but y like it's a constant, right? So in other words, the idea of what's going on here is the following, right? Treat x as the variable and y as constant, because we're treating it like it's not changing, right? Where let's say treating it as if it doesn't change. So in practice, this is what we do. Right? X is the variable. So let's look at an example. Really, really simple first example, 2 of them, right? So if f of xy is, say, x squared plus y squared, we'll say let's look at f sub x of xy. So in that case, right, y is treated as a constant. Is, let's say, considered constant. For the purposes of this derivative, y squared is also constant. So when we take this derivative, we take the derivative of x squared, and that's 2x, because x is a variable. But we take the derivative of y squared, and we get 0. And again, this is because the derivative of y squared is 0, because y is treated as constant. And the derivative of a constant is 0. Now, What if we had, for example, I'll change it ever so slightly. What if we had, say, x squared times y squared? So now the y squared is a multiple, right? This is like if I had x squared times 7, right? So again, in this case, the derivative of x squared is x, the y squared is y, and this is because y squared is multiple, is a product. So if that's a bit confusing, this is kind of like when you do the following. Right? If I had, say, for example, in Calc 1, if I had f of x equals, say, 3x squared, then f prime of x is 3 times 2x. Right? The 3 is just staying. It's multiplied by x squared. There's something called a constant multiple rule, so the 3 just sits there. And I get 3 times 2x, which becomes 6x, which you probably do automatically. But really, that 3 isn't going anywhere. It's staying there as we take the derivative of the x squared. So what's going to happen is, in general, we could take the derivative of a function with respect to any of the variables, and the idea is that we treat that variable as the variable. We treat all of the other variables, maybe there's one other variable, maybe there are 2, maybe there are 10, doesn't matter. All other variables will be treated as constants. So this can take some adjusting, take some getting used to. If you've never done partial derivatives, it can be a bit confusing at first. So always keep in mind, we'll take a derivative with respect to a single variable, and all other variables will be treated as constant. So let me clear the screen and sort of give that sort of abstract definition, and then we'll charge through a whole bunch of examples. So here, in general, we can take the derivative of f with respect to, I'm going to write WRT for with respect to any variable. All other variables are treated as constant. Now there are a few different notations for this, but let's stick with the one that we've done so far. So if we have, say, if f of x, y, z is x squared plus y squared plus z squared, and if we take f sub x, we get 2x plus 0 plus 0. We don't need the plus zeros, of course, but it can help. Right? Now, of course, we could also do f sub y of x, y, z. And now in this case, x and z are considered constants. So we have 0 plus 2y plus 0. And we can also do f sub z of x, y, z. We get 0 plus z squared, because z is the only variable now. So another example, if we have f of xy, let's say, is, say, x times y. Then if we do f sub x of xy, now x is the variable, y is the constant. So you could think of this as like x times 5 or x times 7. So the derivative of x times 5 is 5. The derivative of x times 7 is 7. So the derivative of x times y is y. And the derivative of f sub y, now x is the constant. This is just that constant. I'll do one more and then we'll see the other notation. Suppose we had, say, x over y. Now, in this case, we can think about this. Now, you could do a quotient rule here, but you can also think about this as if you wanted x times 1 over y. Because if we do that, then f sub x, x is the constant, sorry, x is the variable, so 1 over y is constant, so the derivative is that constant. And f sub y, x is the constant, it's multiplied, so it stays there. And then the derivative of 1 over y is negative 1 over y squared. This could be simplified to negative x over y squared. So like I said, this can be confusing at first. The first couple dozen times you do this, it's easy to get confused. That's okay, not a big deal. You'll get used to it eventually. So alternate notation. So instead of writing, so just like with regular derivatives, you can write, say, y prime, or you can write dy dx. You can write f prime or df dx. So here, instead of writing f sub x, we can write this notation. So this looks like a D with a curly top. It kind of looks like a 2 that isn't quite finished. This is not, say, a Greek letter, for example. It's actually a symbol. This is read as partial. So this expression right here, this is read as partial f partial x. Just like if you have, say, this, you would read that as df dx. All right, you wouldn't necessarily say df over dx. You could, it's not wrong. Just like in this case, you could write partial f over partial x, but we don't generally say that. We generally just say partial f partial x, but that's all right. So then likewise, writing f sub y is identical partial f, identical as to writing partial f partial y, f sub z, same as partial f partial z. We want both of these notations. Both of them are useful. So, just like having df dx can be useful and f prime can be useful, don't just think like you want to pick your favorite, because there are cases later on in this chapter we'll see where having one notation will be more convenient than the other. Right? So just to give an example, give 2 examples here. If f of xyz is, say, xy plus xz squared, and partial f partial x. X is the variable, so in the first one we get y, and the second one we get z squared. And I'm taking all of the derivatives, all possible partial derivatives right now, just for exercising. Partial f partial y is x plus 0, and partial f partial z is 0 plus 2xz. And it might take a second to sort of adjust to those. That's okay. I'll give one more over here. If, say, now we don't have to write f. I could write, for example, z equals x squared y. And then you would write something like partial z partial x is 2xy. And partial z partial y is x squared, for example, because now z is sort of, the letter z is sort of taking the place of the function f. So again, the key is that you can do this with respect to any variable. Right? Derivative of f, let me circle this. We can take the derivative of f with respect to any variable that appears in it. But the key thing to remember is all other variables are treated as constants. That's the thing that can be a bit confusing to people initially. So it takes practice. But after you've done sort of a dozen or so of these will be second nature to you, and the mistakes that you make will be far and few between, just like regular derivatives. So there are 2 other things we need to look at. Right? The next thing is, what does this mean visually? Like with the regular derivative, we're finding slope of a tangent line. What are we actually finding graphically when we do this? So there are actually 2 different ways we can look at this. So we'll look at both of those. And then the next thing is to say, like, what about second derivatives? What about third derivatives, etc.? So we'll break that up into 2 things. So first thing I'll do is I'll clear the screen and we'll talk about what these things could represent. And we're only going to do that, well, let me just cross that bridge as we come to it. So we'll say 3, visual meaning. So I'm going to break this into 2 different things, because the first one only works for f of xy. but the second one works for f of xyz as well. You'll see why as we go. Right? So f of xy, we can think of this as a surface, like a paraboloid. So think of this as a surface, like the graph of it. So at a point x0, y0, this derivative, this is the derivative with respect to x. So we're saying, what if y doesn't change but x does? So what this gives us, this is the slope of the tangent line in the x direction. And the second one, this is the slope of the tangent line in the y direction. So let's draw a picture so we can see what's going on here. So what you need to do is you need to imagine the function. Let me draw a function. I'm going to draw a paraboloid, but it could be anything. And I'm going to draw it initially without the axes. So imagine a paraboloid opening down. And this is the graph of f of xy. Now, imagine down here on the xy plane. Let me draw the xy plane as a plane, just as a rectangle. Imagine we go to a specific x0, y0. So imagine this is our x0, y0. And then we take a trip up to the function. So we go up. Maybe we're on the front of the function right here. So this is now the point x0, y0, f of x0, y0. Because we went up to f, right? Now, this thing down here, this is the xy plane. And what this means is that this is the x direction coming forward. And this is the y direction going to the right. So what's happening here is, suppose I'm at the purple point, x0, y0, f of x0, y0. And I head in the x direction. Right? Now, because I'm sort of on, at least the way I drew this, I'm on the front of this paraboloid. If I head in the x direction, I'm going to go downhill. So in the x direction, this tangent line slopes down. Because remember, positive x's come forward. Right? So what this means is, in this case, that f sub x of x0, y0 would be that negative slope. Let's just say would be that slope. Now we'll do an example in a second, but just so that we see. Now, if I have the same picture, so let me replicate that same picture again. So I paused it while I recreated the picture, so we didn't need to recopy the whole thing, didn't need to watch me draw it. Now if we're at this point and we go in the y direction, in this case we might go downhill too, maybe it'll be a little less steep. So if we go in the positive y direction, what we would say is in the y direction, this tan line slopes down again, according to this picture for this particular example. But the key is that f sub x, or f sub y of x0, y0 would be this slope. So, right, what we're doing is we're getting the slopes of two tangent lines. One is in the positive x direction, one is in the positive y direction. So if we go through an example just so that we can see. Now, of course, this is it's a hard problem to draw a graph of, especially if the graph is not something pretty. So if we have something like f of xy equals, say, xy plus y squared, we have no idea what that looks like. But we can still do the calculation, right? We can find f sub x of xy, and we can get, in this case, y plus 0, just y. We could do f sub y of xy, which is x plus 2y. And then we could say, for example, at the point 1, 2, f sub x of 1, 2. Now f sub x is just y, so this is 2. This is the slope in the x direction. Now we can take f sub y of 1, 2. This is x plus 2y, so this is 1 plus 4 is 5. This is the slope in the y direction. So at the point 1, 2, if you go in the y direction, or sorry, in the x direction, the tangent line has slope 2. And in the y direction, the tangent line has slope 5. It's steeper in the y direction. Now, this is a really useful graphical way. There's another way of looking at this that's also really, really interesting. So let me give that, and the advantage to that is it works with f of x, y, z, and is sort of a little easier, I think, to wrap your head around. So I'll clear the screen off and we'll do that one. So again, we're going to look at f of x, y, but again, this will work for multiple dimensions. So one way that we said that you could think of a function was giving like a temperature at a specific point. So let me look at a specific example. Suppose f of x, y equals, let's go back to this xy plus y squared. We'll say this gives the temperature in degrees Celsius at xy, where a scale is in meters. In other words, the xy scale is in meters. All right, then let's run through it again. F sub x of xy is y plus 0. Let's just write y. And we can write, say, f of x of 1, 2 is 2. And f sub y of xy, it's the same calculation as before, is x plus 2y. F sub y of 1, 2 is 5. Now, while we're at it, we'll just note that f itself at 1, 2 is xy, which is 2 plus 2 squared, which is 6. This tells us the following, right? If we were to just draw regular xy plane, and we go to the point 1, 2, right? What we can say is we can actually say three things about this point. Like at the point 1, 2, we can say the temperature there is 6 degrees Celsius. That's because that's what F tells us. Then we can say, aha, yes, if I go to the right, if I go in the x direction, the temperature change is 2 degrees Celsius per meter. That's an instantaneous temperature change. That comes from right here. Whereas if I go in the y direction, let me pick a different color. In the y direction, the temperature change is 5 degrees Celsius per meter. And that's because of this. So this is like a really nice way of thinking about it, because of course this works in 3 dimensions as well. I won't necessarily do an example, but the beautiful thing about this is works for f of x, y, z as well. Like, in other words, it works for as many dimensions as you want, but it makes sense for 3 dimensions, right? You could think about temperature at a specific point, and you could ask what happens if you go in the x direction, the y direction, and the z direction. How does that temperature change? And it all works out nicely. So it's a really useful way of thinking about it. So, very last thing to look at then is higher derivatives. Specifically, second derivatives, third derivatives, etc. We'll only go to second derivatives. That's all we need to do to second partial derivatives. Now, these aren't hard. It's procedurally very simple. There are just two things to point out. One is how many different second partial derivatives there are, and two is a notation thing. So there are two, let's say, things to be cautious about. So let's look at an example. And the example will illustrate both of these things, as well as the notation. So suppose f of xy is, say, x squared y plus 1 over x. Now, we can do two different first derivatives. I could do f sub x, which is 2xy minus 1 over x squared. And we could do f sub y, which is x squared plus 0. Now, once we've taken each of these, what we can do in each case is we can take another derivative with respect to either variable. So, we did it with respect to, in this case, we did it with respect to x first. But the second time doesn't need to be x again. It could be x again, could be y. In the second case, we did it with respect to y, could be y again, could be x again. Which means in this case, in each case, we have two possible next steps. So there are 4 second partial derivatives, or second partials, if you like. Right, the word partials is sometimes used to mean partial derivatives. So let me do all of those. Let me clear the left-hand side. I'll leave the right-hand side. I'll clear the left-hand side, and we'll work through all of those. So here are the possibilities. So from this f sub x that we did, right, once we've done that, we can do x again. So the notation here is f sub xx. And so we'll talk about the order of those letters in a second. So what I'm going to do is I'm going to take this function above and do the derivative with respect to x yet again. So the derivative of 2xy with respect to x is 2y, and then plus 2 over x cubed. Or we can then do y. So notice in the notation here, what's happening here, this is read from left to right. This is x, then y. It's building out from the f. Now, if I do it with respect to y, then we would get 2x minus 0. Those are our two possibilities. Or, from the other one, f sub y of xy, which was x squared, this is really, really easy, we can do either f sub y again, which would be 0, or we could do y and then x. So again, the key thing to see here is we're doing y then x. And if we do that, we get 2x. Now, for the last few comments, because there are two things to address. I want to address the notation for the other notation, the partial notation, because it's a bit different. But I want you to notice something here, because you might, if you have a keen eye, you might say, well, look, these are the same, right? You might ask yourself, is it always true that f sub xy is the same as f sub y x? The answer, right, you cross your fingers and you hope it's yes. The answer is almost always, right? You can almost always take it for granted. I think, for example, in the course textbook, there's one example of one problem in an obscure place where it's not true at a certain point. So you really have to go out of your ways, right? So basically the answer is pretty much yes, right? For all intents and purposes. Yes. In other words, in this course, you can pretty much assume that they're the same, which is nice because it means if you did them in the wrong order, you're pretty much safe. Not a big deal, right? So a couple closing comments. One is, what about the other notation? So let me clear the right-hand side of the screen, and then we'll mention that. So note 1, alternate notation. So in place of f sub xx, we could write partial squared f partial x squared, right? Now, this may seem a bit weird, but this should remind you of, Calc 1, little side note here. In Calc 1, we have partial f partial x, and for a second derivative, we have partial squared f partial x squared for a second derivative. So this is running parallel to that, right? It's basically the same, right? And likewise, in place of f sub y, we could write partial squared f partial y squared. Sorry, it's terrible too, for the same reason. Right? However, the two places where it's confusing is in place of f sub xy, we could write partial squared f partial y partial x. Right? Now, if this bothers you because you're like, hey, wait, the x's and the y's are sort of the wrong way round, like in the with the f we had f sub xy, but here we have partial y partial x. So this is, if this bothers you, this is because what we're doing is this. Right, we're taking it with respect to x first, and then with respect to y. Right, this notation works by putting the partial y on the left, and so when you jam these together, they reverse order. Right, so this is x then y. Whereas in this notation, it was x then y because we built it from the left to the right. So again, the convenient thing is it doesn't matter. Typically, like the pink note to the left suggests it doesn't matter the order that you do it. So really, if you do it in the wrong order, it's not the end of the world. It's pretty much going to be the same, but it's good to get the notation clear. So likewise, in place of fyx, we could write partial squared f partial x partial y. Because, again, this is identical to if we wrote it out a bit longer and wrote this. Right, y first and then x. So the only other last note I want to give, let me actually do an example just to point it out. So let me clear the screen off and give that note, and I'll just give one closing example. So note 2 is just to keep in mind, if you have something like, and we won't really encounter this a lot, but it's just to keep a good sense of perspective. Right? In this case, there are actually 9 second partial derivatives, because you could do x then x, x then y, x then z, y then x, y then y, y then z, and so on. I will pretty much never ask you to find all 9 of these, right? And if you had f of x, y, z, w, you'd have, even more, you'd have 16. So it can be pretty crazy. But just to give you an example, I won't do all 9, but just to see how icky it gets. If you had like xy over z plus, say, xyz. You can take 3 first derivatives. I'm going to not worry about the parentheses right now. All right, so you can take the derivative with respect to x. So you get y over z, because x is the variable, plus yz. You could take f sub y. Now y is the variable. I get x over z plus xz. F sub z is a little trickier because z is in the denominator. So this is negative xy over z squared plus xy. And then you can go even further, right? You could do, for example, f sub x, which you take this guy and you do x again, which is 0. Or you could take f sub xy. You take, again, that first one again, and you do y. So you get 1 over z plus z. Or you could do, for example, just to make this up, zx, which means you go to z and you do it the derivative with respect to x. So negative y over z squared plus y. So these can get messy, right? These really, really can. So the key word is practice. Right. After you don't do a bunch of these and you make all the regular mistakes, just like when you learn how to take derivatives, you'll practice, you'll get used to them, and you'll start to see the patterns. So that's the end of that section. So we'll call that done.